Let's look at the instantaneous centers of zero velocity in example 16.9. No numbers here, sorry guys. We're looking at like a crankshaft, piston rod, piston cylinder assembly, and in this case we have some omega of AB given to us. BC is going to have its own motion, and we should notice that the velocity of C is going to be constrained in the I direction. Let's take a look at the other paths though too. This is on a circular path. The other one is on a straight path like this. And let's connect the dots. Alright, so that's what BC is doing. It is moving with some velocity at C here, and if this is a circular path, this has to have some tangential velocity at B. Alright, find the instantaneous center of zero velocity. I'm going to trace a perpendicular from each velocity. They're not parallel, so no special case. Draw one out that way, and whoop, looks like we're going to have some interference. The other point is drawn perpendicular as well, and we can find our instantaneous center right there. And then you can get use the relationship. The whole point of this is to reduce the velocity of B is equal to the velocity of A plus omega crossed B with respect to A. We can get rid of this term if we look at the point where there's no translation. What about if we have, here's your calculus problem where you have the ladder or something, which is our rigid body in this case, sitting up against a wall. We can call this A and this B. In this one it doesn't really matter because A and B are both translating. A is going to have some motion directly down, and B is going to have some motion directly to the left. And if I draw my perpendiculars, I find my instantaneous center right here. Okay, let's do one more. Okay, we have, oh, wrong color. Draw a reference line. Alright, so we have one arm and then we have a slightly longer arm. The point is that they're both exactly horizontal at this moment, and since they're horizontal, even though they may both have different circular paths, one's going to have a larger circular path than the other, at this instant they have velocity vectors that are pointed straight down, and they would both be equal to each other. So we cannot extend any lines, we cannot have any intersections to find us the instantaneous center, because there is no instantaneous center. At this instant, there's no rotation. Now, and sorry, there's a member there. At the next instant, when this moves down and this moves down, we're going to undergo some rotation. Looks like it's going to be in that direction is our omega. But at the instant considered, which we do a lot of in these problems, we have to look at the instant that the geometry is given to us. They're parallel to each other, but they are also the same length. These run all the way out to infinity. We cannot make perpendiculars that intersect, so we have no instantaneous center of zero velocity.